Measuring three-phase power. In this presentation, we're going to look at how we measure the true power that is being consumed by a three-phase load. And in order to do that, we're going to have to use watt meters. Now, watt meter, for those of us who are unaware, is a 3 or 4 terminal device that has a series connection for an amperage measuring component and a parallel connection for a voltage measuring component. And what the watt meter does is it multiplies the two values together and it gives us the watt value of the load. In a three-phase system, the watt meter amperage or current connection will be in the line conductor. The voltage connection will either connect to neutral or an adjacent line conductor, depending on the required connection. So that then brings us to how many watt meters do we actually need? Well, the number of individual watt meters used is dependent on a couple things. The first factor is that the load being balanced or unbalanced. This will have an effect on how many watt meters we use, and if the load is Y or delta. Now, our total choices are 1 or 2 or 3 watt meters. So let's look at the most basic type of watt meter connection for a three-phase load. The first one we're going to look at is a single watt meter installation. Now, a single watt meter is of limited application in the field because it can only be used on a balanced Y load. And to make things even worse, it needs a neutral in order to function properly. In order for this to actually provide us with some meaningful data, I've got a phase voltage connection here telling us what the phase voltage is of this load. And we know from our power formulas that if it is balanced, I can simply multiply that value by 3 to get the total watts. Now, if the load is balanced, it's highly unlikely you're going to have a neutral connection available. And so this one is really of limited use. It needs a neutral, and there's no way for us to determine power factor with only 1 watt meter. Okay, well, let's then swing to the other side of the spectrum and take a look at a 3 watt meter installation. Now, a 3 watt meter installation is able to accommodate both balanced and unbalanced, but still only Y loads. So the 3 individual watt meters are again connecting to the neutral, providing phase voltage for the watt meter, and we've got essentially phase current here, which means that it's measuring individually the power on each phase of this load, and we simply add them together in order to get the total watts. Now, in this situation, I need 3 watt meters, which can be quite expensive. It needs a neutral, and the power factor is unknown. Again, it cannot tell me what the power factor is of the three-phase load. Well, there must be then a better solution or alternative. We've looked at a single watt meter and we've looked at 3 watt meters. What about 2 watt meters? 2 watt meters has its place when it comes to energy measurement, and it can be used in a balanced or an unbalanced Y load. So exactly the same loads that we discussed in the previous slide. But notice what's happened now. I have reduced the total number of my watt meters by a third. I only need 2 watt meters now instead of 3, and I still get the exact same information. In fact, there's a few benefits. So first off, you'll notice that the watt meters are now connected to, well, still line current here, or phase current, if you wanted to phrase it that way, but the voltage connects to the adjacent line conductor. And so the higher voltage value here is going to allow us to determine the total power of this three-phase load with only 2 meters. So the way that we add up the total is we simply get the sum of the 2 watt meter values being displayed. Now here's another advantage, no neutral needed. And here's another advantage. It can calculate the power factor if the load is balanced. So if we happen to be measuring a balanced load, we could calculate the power factor. It's a bit of a behemoth when it comes to equations. Here it is. Watt meter 1, watt meter 2, you subtract, you then add them, you then multiply by 1.732, you apply inverse tan, and what this ends up giving you is the phase angle of the entire three-phase load. If we then apply cos to the phase angle, we should come out with the power factor of the total three-phase load. Now, is this something you would do on a regular basis in the field? Oh, goodness, no. No, no. You would not be applying this calculation in the field. But what you will find, depending on the size of the application you're working on, 2 watt meters being used, and this is known as the 2 watt meter method in the electrical industry. Now, we haven't even talked about delta loads. So let's take a look at delta loads. And this is really where we start to see that the 2 watt meter method is the adopted standard for energy measurement on three-phase loading. I still only have 2 watt meters. The connections have not changed at all for my watt meters. They are measuring the line current of my load, and they connect with the voltage connection to an adjacent line conductor. I am still able to determine the power factor of the load if the load is balanced. So out of all three of the different options, 1 watt meter, 2 watt meters, or 3 watt meters, the 2 watt meter method is by far the more adopted and more prolific in the electrical industry. Well, let's then take a look at a few basic examples utilizing some of this information. So this one here, we've got a three-phase load and it has the following watt meter readings. So it says W1 60 watts, W2 100 watts, W3 is 80 watts. Well, with this information, we can then start answering a few of the different questions. So there we are with my little pamphlet here. What type of load configuration are we dealing with? Well, if it's 3 watt meters, it means it has to be a Y configuration. And if we wanted to know the total three-phase power, well, we simply add all three of the watt meter values together. So 60 plus 100 plus 80. Okay, well, let's take it a step further then, and let's determine what the power will be for a 2 watt meter installation on a different load. So this one here, oh, it doesn't really work out so well, but there we go. Oh, there we go. So a three-phase load has the following watt meter readings. It's balanced, so they've just told us it's a balanced system. Watt meter 1 is 515, watt meter 2 is 860. So what's the total three-phase power? Well, we add the two values together. We get a sum. Gives us 1375 watts. Now, what's the total three-phase power factor? Now, remember, this only works with a balanced system. And really, it's only going to tell us the numeric power factor, not necessarily if it's leading or lagging. You would have to bring that information with you to the calculation. So we are first going to have to go through all of this. We subtract the two values, add the two values, which gives us this. We then divide the two values, gives us this. We then multiply by 1.732, gives us this. We apply inverse tan. That gives us a phase angle of negative 23.488. So that's the phase angle of the three-phase load. We want to know what is the power factor. And the power factor then, we need to apply cos to this number, and we get a power factor of 0.91. So 2 watt meter method, not a very common application to actually determine the calculated power factor, but it is possible. Do we know if this is leading or lagging? No, I don't, unless I can see what the loads are. If I see that it's motors, then I know that it's inductive. If it is part of a larger capacitive correction system, I should still assume it's inductive. Really, the only reason it would be leading is if we had a problem with a synchronous condenser or something that's providing variable leading VARs to the system. But I digress. Finally, let's look at another example. And this one, a three-phase load has the following watt meter readings. It's 1 watt meter, 1,000 watts. And there's only one, it says. Well, based on this, we know the load configuration has to be Y. Is it balanced or unbalanced? We know it has to be balanced. And finally, what's the three-phase power? Well, we can multiply that one value, 1,000 watts, by 3, giving us 3,000 watts.